Hello, welcome back. Today I'm showing you the math behind the space elevator. In a previous video I showed the representation of the space elevator and how it should look like. The space elevator is divided into three main parts. Firstly, the cable, that is this part. We will see the materials we can use to cope with the stress and all the problems that carry. The next part is the counterweight. This is an optional part and enables us to use a shorter cable. And the last part is the climber, that it is the main part. We will carry the material, whatever we want to deliver in orbit. The space elevator is the attempt to build an elevator that enables us to the atmospheric escape. The space elevator is based on centripetal forces principles, and we will see now the calculations. The gravitational force should be less or equal than the centripetal force. So now we can calculate each one and see the length of the cable used. First, the gravitational force. We can use this formula. However, there is a problem, because if we draw this, if we draw the cable around the Earth, we have a problem. The gravitational force in this point is different than in this point or this point. So what can we do to measure the overall gravitational force? We can do the integral of the gravitational force. But if we do that, we obtain the potential energy, and we don't want that. So the next thing we are doing is divided by the total length, that it is going to be called x. So we follow this formula, and this is the result. The integral between r, that is the Earth radius, and r plus x, that is the Earth radius plus the length of the cable, and the universal gravitational force. We integrate with respect to x with r, and then we divide it by x to get the average gravitational force. We are now going to calculate the gravitational force for the spring, and we omit the satellite, the counterweight, if you want to call it like this. So the next step is to calculate the centripetal force. As you may know, the centripetal force follows this formula. However, if we want to calculate another time the centripetal force for the entire cable, the whole cable, the centripetal force is variable and is different in all the points. So we make another time the integrals, and then calculate this. However, we have a problem, because the velocity, if we integrate this, we have two variables that are not constant, that is the velocity of the cable and the radius. So we can, as we know, the velocity is the angular velocity multiplied by the radius. and we know that the angular velocity of each point is constant, so we substitute the v in this equation and we get this, and now we only have to make the integral. In this step we also meet this force because it complicates the calculations. Now we operate and see that the x should be greater or equal than 1.44 multiplied by 10 to the 8th power. If we have a length of the cable that is greater or equal than this, we know that it will be used as a space elevator. Here we see the graph that we've used. The gravitational force with respect to the radius. This is the gravitational force, and we see that the start point is r and the finish point is r plus x, and we want to calculate the average gravitational force, that will be this. Okay, we will call this AB. Okay, so now we have isolated the x value. We have solved all the equation that is a little bit complex. If you want to see the median steps, I have skipped these steps because they are a bit tedious, but if you want to see it, you can search in my website that is called theprogrammer.org. You can search it in Google, theprogrammer.org, and if you click in the space elevator post and you scroll down, you can download the paper that explains step by step all the calculations and solve the equation. Or if you want to see it in the website, it is here. So that's all. I hope you like this video and see you in the next video.